Hi everyone, in today's presentation we'll be talking about linear discriminant analysis. Linear discriminant analysis, or LDA, was developed in 1936 by Sir Ronald Fisher. It's essentially a generalization of Fisher's linear discriminant functions, which were designed to address multi-class classification problems. By projecting data onto a lower dimensional space, LDA helps us identify patterns in data that distinguish between different classes. The core idea behind LDA is that it first maximizes the between-class variance, which makes sure that the data points from different classes are as spread out as possible, and then it minimizes the within-class variance, which tries to reduce the spread of data points within each class, ensuring that similar data points are grouped together. Altogether, this process allows us to project the data onto a new set of axes, where the most important features for distinguishing between classes are highlighted. In other words, it simplifies the data while maintaining crucial information for classification. LDA has various applications in real-world scenarios, particularly in machine learning and pattern recognition. One of its key strengths is its ability to optimize models for multi-class classification problems, and it does so by reducing the dimensionality of the data. An example of a usage is face recognition systems, which work by reducing the high-dimensional data from face images while retaining the key features that distinguish one face from another. And this leads to more efficient and accurate recognition algorithms. Another application is in quality control and defect detection. LDA can be used to classify products as either defective or non-defective based on various attributes or measurements. In industries like manufacturing, this helps in identifying issues quickly and efficiently, ensuring that only high-quality products make it to the consumer. Before we talk about how to apply LDA, recall that LDA is only used when you have labeled data, meaning each data point in your dataset already has a known class or category. For example, if you are working with a dataset of customer features like age, income, and spending score, and you wanted to classify them into categories like high value or low value, this would be an appropriate use of LDA. So again, you want to ensure that your dataset has multiple features or variables that can help differentiate between the classes, and that you have at least two or more classes in your data. The first step in LDA is to compute the mean of each class in the dataset. Let's say you have a dataset with P features and N data points. And let's call the original data matrix X with shape N by P and K classes. For each class K, we compute the mean vector mu sub K, which is the average of all data points in that class. And mathematically for K, the mean vector is this formula over here, where N sub K is the number of samples in class K, and X sub I represents the data points belonging to class K. Similarly, the overall mean vector is computed using this formula over here, where n is the number of data points. Next, we calculate two types of scatter matrices. We have the within-class scatter matrix, which is S sub W, and that represents the variance within each class. And it's computed by summing the covariance of each class. For each class K, the within-class scatter matrix is given by this formula, where K is the number of classes and mu sub K is the mean vector of class K. We also have the between-class scatter matrix, which measures the separation between the different class means. It's computed as a weighted sum of the differences between each class mean and the overall mean mu. The between-class scatter matrix is given by this formula, where n sub K is the number of classes in class K, and mu is the overall mean of the data set. So our next question is, what do each of these elements represent? Let's say the dimensions of the scatter matrices are 2 by 2. For the within-class scatter matrix, the diagonal features, which would be S sub W11 or S sub W22, would be the variance of feature 1 and 2 respectively. And then the other elements, so S12 and S21, would be the covariance between features 1 and 2. And the between-class scatter matrix would have a similar outcome, where S sub B11 would be related to the difference in mean of feature 1 across classes relative to the overall mean. S22 would be related to the difference in mean of feature 2 across classes relative to the overall mean, And then S12 and S21 would measure the covariance between features 1 and 2 across classes based on the difference between class means and the overall mean. Now that we have the scatter matrices, the next step is to solve a generalized eigenvalue problem. Recall that eigenvalue problems are helpful for optimization. Again, we're optimizing the separation between each class, so this would make sense that we have S sub W. And then it also makes sense that we have the inverse of S sub W because we're trying to minimize within class variance. We want to find a transformation matrix W in order to do so, and that's solved by solving the following equation. Here, W is the eigenvector corresponding to the eigenvalue lambda, and the matrix, the inverse of S sub W times S sub B, and the eigenvectors represent the directions that maximize class separation, and the eigenvalues represent the magnitude of separation along these directions. Once we solve for the eigenvectors, we can choose the top k-1 eigenvectors, where k is the number of classes. And for now, let's just call k-1d, and these eigenvectors form the transformation matrix W. We then project the original data points onto the new lower dimensional space by multiplying the data matrix X by the transformation matrix W. In the next slide, we'll see an example of transforming a 2D data to 1D. And this is done so by creating the new axis, again, maximizing the distance between means and minimizing variation or scatter between each category, and then projecting the data onto the new axis. For this example, we'll look at the iris dataset. Our goal is to classify information about 3 species, Iris setosa, Iris versicolor, and Iris virginica. The overall dataset has petal and sepal length and width, but for the sake of time, we'll focus just on the petal length and width. Let's say the number of data points in each class is 50, and we have the summary statistics, or the mean of each feature. And given these class means, we can compute the overall mean. Also, using the formulas from the last slide, we can compute the within class and between class scatter matrices. Next, we'll compute the eigenvectors and corresponding eigenvalues for the scatter matrices. Again, we're solving the inverse of S sub W times S sub B times W equals lambda times W. We can first compute the matrix, then solve, and the resulting 2 eigenvalue/eigenvector pairs are 7.1 and 0.7. Recall that we're picking k-1 eigenvalue/eigenvalue pairs, and k is equal to 0, so we just pick 1. We also pick the larger eigenvector, since that represents a larger magnitude of separation. Thus, we'll pick the eigenvector 0.8, 0.6 with the corresponding eigenvalue 7.1. Now we'll apply the transformation vector W sub 1 to the data matrix X. This obtains 1.32 as the mean for the setosa species, 4.16 for the versicolor species, and 5.96 for the virginica species. Now looking at the 2 graphs here, we can visually see what's happening. So we start off with a scatter plot, and determining the separability of the classes is difficult because there's a lot of overlap. And one bad approach we can take is simply projecting to the x-axis downwards, which is petal length. However, that loses information about the petal width, and again, we know that more information about more features helps with separability, so we can't do that. The alternative here, which we achieved with LDA, is to create an axis, then project the points onto that axis. And you can see that in the dotted line, for example, as an axis, and the results of that are on the right. Ignore that the mean values are slightly off. These data points are randomly generated, since the process by scratch takes a lot of arithmetic. And although there's still some overlap between versicolor and virginica, it's much better than what we started with. Setosa and versicolor are very separated though, which is good. And the spread is also minimized, and the means, which we can see circled in black, are also separated. Even though we just focused on a 2D to 1D transformation, for the sake of visualization, the process is the same for higher dimensions. We create a higher axis, that maximizes distance between means while minimizing the within class variance. And yeah, with that, I conclude my presentation. Thank you all for listening.